the limit comparison test is similar to the direct comparison test, only instead of comparing two series directly with each other, we're going to look at the limit of their quotient. So suppose that we have two series, A sub n and B sub n, and that they're both positive. And then suppose that the limit of A sub n over B sub n, or the limit of B sub n over A sub n, equals L, where L is a positive and finite number. If this happens, then the two series will both either converge or both diverge. So if we pick a good series to use in this comparison, like we did with the direct comparison, if we know that it diverges and the limit of the quotient of the two series is a finite positive number, then we would know that whatever the series does that we picked, if it converges, the other one would converge. If the one we picked diverges, then the given one would diverge. So it's another pretty simple test. The limits can get a little messy because you might end up having all these compound fractions, but we can work with that. That's not a problem. So let's do an example. So example 1, determine the convergence or divergence of the sum from n equals 1 to infinity of the square root of n over n squared plus 1. If it weren't for that plus 1, this wouldn't be a difficult series to determine what's happening, but that plus 1 sort of messes everything up. So I'm going to pick another series that is similar to this one, and in fact I'm going to pick the square root of n over n squared. I'm just going to strip off that plus 1. Okay, so and to make my life a little bit easier, if I can even rewrite this would be n to the 1/2 over n squared, and that's going to work out to be 1 over n to the 3/2. Alright, so now we want to take the limit as n approaches infinity. And it doesn't matter which one I put on top, which one I put on the bottom. I'm just going to start with my given one first. The square root of n over n squared plus 1 over 1 over n to the 3/2. That's a really gross and disgusting limit. I don't like it. So instead of leaving it as dividing by a fraction, I'm going to rewrite it so I'm multiplying by the reciprocal. So the square root of n plus over n squared plus 1 times n to the 3/2 over 1. And n to the square root is just n to the 1/2 times n to the 3/2. So that would be, and I'm going to come write it down here, the limit as n goes to infinity of n squared over n squared plus 1. And then suddenly, all of a sudden, we have something that's very easy for us to take the limit of and to tell what's happening. This would equal 1. 1 is definitely positive and a finite number, and so what that tells me is that whatever the series that I chose, 1 over n to the 3/2, whatever it does, then the one I was given, the series I was given, will do. Okay, so you just need to determine what 1 over n to the 3/2 does. Well, 1 over, and I'm going to go ahead and call this b sub n and let the one I was given be a sub n. Okay, so as long as I label that as b sub n equals, okay, equals, then what I'm going to write is b sub n is a convergent p-series because p is greater than 1. There you go. Therefore, a sub n converges by the limit comparison test. And I didn't put it in the notes, but yes, you may call this the LCT. Okay, so pick a series, take the limit of the quotient of the two series. If it comes out to be positive and finite, then whatever the one you chose does, the other one will do it as well. Now, I didn't double check, I didn't go through the motions of checking that the two series would be positive, you really do need to go ahead and do that. And so I would, in my work, show that a sub n is greater than 0 and that b sub n is greater than 0. And you could do it all in one statement, and that's fine. The other thing that I haven't really mentioned much as I've gone through these videos is you're not going to jump right into the limit comparison test. Really, the first thing you ought to do with this is do the nth term test. It'll tell you real quick if it for sure diverges, and it's a quick way to check for divergence. Of course, you know, it may not work for us, and in this case it wouldn't, because in this case the limit of our series does equal 0, so then it's inconclusive. That's when we would then move on to another test such as this limit comparison test. So do check your other tests first before jumping into these that are a little bit more complicated. All right, I have one more example. So let's look at example 2. Determine the convergence or divergence of the series from 1 to infinity of n times 2 to the n over 4n cubed plus 1. Notice that these series are all starting to get a little more complicated, and that's going to keep happening as we go along. So don't let these kind of freak you out. Again, the easiest way to go about picking, well, hold on, let's start first. If I do the nth term test on this one, then I would end up with taking the limit of this, and this would actually end up being a divergent series by the nth term test. Okay, so do that and you can be done. But we do want to go ahead and do this by the limit comparison test, just to show you how this works. Okay, so the first thing I want to do is verify that this is a positive series, and it is. N is positive, so the numerator is a positive times positive, and then the denominator is going to be a positive plus a positive, so it is in fact a positive series. And so I'm going to go ahead and label it and show that that's supposed to be a 0, greater than 0. That's just terrible. Let me get my eraser. One of these days I'll learn how to write on this thing. Okay, and now I need to go ahead and pick a series that is similar, and so in this case I'm just going to strip away the extra thing. So I'm going to take away the 4, I'm going to take away the 1. The other thing that I'm going to do is resolve the n over n cubed, and so I'm going to let b sub n be the series from n equals 1 to infinity of 2 to the n over n squared, and that's because n over n cubed is going to become n squared. So that's what I'm going to work with. Okay, that's a positive number raised to an exponent over a positive number being squared, so this is in fact greater than 0 as well. So we're good with the requirements at the beginning of the limit comparison test. So now we want to go ahead and take our limit. So our limit as n approaches infinity, and again, remember, it doesn't matter which one you put on top or bottom. I like to put the one I'm given because it tends to be the more complicated one, and that way I don't have to mess with trying to multiply by the reciprocal of it. Okay, and then you can go ahead and show over 2 to the n over n squared, or if you want, you can just go straight to this step and write the multiplication one, so we would have n squared, n squared over 2 to the n. All right, so let's simplify this. Okay, the 2 to the n's are going to cancel out. Then we'd have n cubed, so we've got the limit as n goes to infinity of n cubed over 4n cubed plus 1. That's a lovely limit for us to take. It's going to be 1/4. So that is positive and finite. So we are good on that the second requirement. We have positive series, we have two positive series, and we have a limit that is positive and finite. So the last thing we needed to do is to determine whether or not our B sub n converges or diverges. So if we look at it, B sub n, the first thing I would do is I would go ahead and do the nth term test on B sub n, okay? And what I see, 2 to the n over n squared, that top is definitely going to grow a whole lot faster than that bottom is, and so that's going to go to infinity. It is not going to 0, and so therefore B sub n diverges by the nth term test. So A sub n, which we can write that because we named our series up there A sub n, not equals, but diverges by the limit comparison test. All right. Do the problems. Let me know what questions you have. Y'all have a good evening, and I'll see you tomorrow.